Hello and welcome to Econometrics with James Bland. Today I'm going to be running you through a simulation problem from my Econometrics notes. I'll post a link to those in the video. And this simulation is going to explore the properties of instrumental variables and specifically two-stage least squares when you have either weak or bad instruments. Okay, so I'm going to do this in Stata, and firstly I'll show you the simulation exercise from my Econometrics notes. Okay, so Bailey is the text I usually use, I'm using at the moment. Anyway, here's a direct quote from Bailey. A weak instrument does a poor job of explaining the endogenous variable. Weak instruments magnify the problems associated with quasi-instruments and can cause bias in small samples. Okay, so even if your instrument is uncorrelated with the error term, if it doesn't predict X very well, you're going to run into some problems if you have small samples. Okay, so we're going to explore this today. Specifically, we're going to simulate the sampling distribution of our two-stage least squares estimator using the following data generating process, which looks like this. Okay, so we're going to generate our y, which is just going to be equal to x plus an error term. And then we're going to generate our x that's going to be equal to this combination of all of these instruments plus an error term. And then we're going to generate a whole lot of z's, well 5 of them, that are all standard normal and they're independent. Okay, so all of these instruments are uncorrelated, well, must be uncorrelated with the error term in the equation for y, but we're going to have some problems elsewhere. Okay, now let's have a look at the eta terms at the moment. Here I've got I've defined these etas as coming from a multivariate normal distribution with mean 0. I don't really care about the mean, but this is the variance-covariance matrix. So on the diagonal here, this says that the variance of all of these error terms is 1. Again, not particularly interested in this. What I am interested in is the correlation. Okay, so here we have eta 1, so this is the error term that appears in the equation for y, is correlated with eta 2, which appears in the equation for x. That's our, that's our endogeneity problem. And it's also correlated with eta 3, which is our z6, right? So z6 is actually not a valid instrument because it fails the exclusion condition. Okay, and so that's why I have these etas in here. We're going to simulate this data generating process and simulate beta hat from two-stage least squares under the following conditions, right? So we're just going to use z1 as an instrument, then we're going to use z1 through 5 as instruments, then we're going to use z1 and z6, and then we're going to use all of them. Okay, and we're going to look at the distributions of these, the estimators, using these sets of instruments. Okay, but to begin with, what I'd like to do is to draw the directed acyclic graph for this data generating process. And so I'm going to go back to my notepad. Okay, here we are. So here's the data generating process as specified in my notes. And in particular, we're interested in how does x cause y? So this is going to be our beta hat that we want to estimate, or our beta that we want to estimate. And now we have, well, let's draw the etas into this graph. Okay, so we have, how are we going here? Eta 1. So e to 1 causes y. Then we have, if we look here with x, z2 up to z5 don't enter into the equation for x. I just put the zeros in there to show you that, you might think about using these in term as your instruments for x, but they don't actually satisfy the inclusion condition. So we know that z1 causes x. We know that e to 2 is going to cause x because it shows up in the equation here. We know that z6 causes x. Okay, but we also know that e to 3 causes z6, and there's some common error term between e to 2 and e to 3. Okay, so that this common error term, I should probably switch to another, no, maybe I'll finish labeling them out. This is the correlation between e to 2 and e to 3, so that's this one here, and I also need a correlation between e to 2 and e to 1, so let's call this gamma in here is correlated with these two. Okay, and so the problem is the problems we have are that we have a backdoor pathway between x and y. Okay, so that's why we can't just run OLS, and we also have this correlation between the error term in x and the error term in z6 that means that z6 isn't a valid instrument. Okay, so I'm setting up this problem so that, we're running a simulation, so we know what the true data generating process is, but we're going to explore what's going to happen if we run various different kinds of, or include various different sets of instruments on the right-hand side of our first stage. Okay, and so when I run you through this simulation, I'm going to do it as I do in class, where I give my students 3 steps that they should try to do rather than just coding the thing up in one go. So the first step is, actually I'll need a bit more space. The first step is get one stage of the data generating process going, or DGP going. Step 2, get this into a program that works. And then step 3, run simulate, which is a static command. Okay, and the reason I get my students to do it this way is because going from step 1 to 2 then to 3 is a reasonably logical way of doing it. It's not going to mean that you spend wasted time on things if you know what's going on, but it also allows you to check your script for errors as you go through. So you'll find out where the errors are, rather than just coding the whole thing up in one go and thinking, oh, I've got a whole lot of red coming out into my output window. What does that mean? It's hard to find where the error is. And then you're probably going to end up going back to here and starting here anyway. Okay, so I'm going to move over to Stata now and start coding up this problem. Okay, let's go over to Stata. Here is the problem again, and so we're going to simulate this process for 1,000 observations. So remember the original claim in Bailey, this is a reasonably general result. is that it can cause bias in small samples. And I've picked 1,000 here because, well, I can get this to break at n equals 1,000, and it's not really a small sample, and you're going to see that we still have a problem. Anyway, let's not do this. I have too many Stata windows open again. Here we go. Okay, so here is my empty script. Okay, so originally the problem, or the exercise asked us to simulate this for 1,000 observations. So what we need to do is to create a data set that is expecting 1,000 observations, and then we're going to populate that with our random draws. So to do this, we do set obs 1,000. And we can see here the number of observations is 1,000. If I open up my data editor, we can see here that I've got, it's a bit hard for you guys to see, but it's blank, but it has 1,000 rows in it, if I actually wanted to scroll down there. Okay, so now let's go back and have a look at problem set. What are we going to do to start off with? Okay, so Z1 through Z5 are just IID normals, so I'm going to generate those. Okay, so for values I equals 1 to 5, do this with copy and paste, but I don't really like that. Generate Z I equals R normal. Okay, so if I run this and then I'll just have a look at my data. Well, I haven't started my for loop. Let's have a look at my data now. Okay, so now I have these variables all the way up to 1,000. If I go back to the start, how about we just list the first 10? And 1, 10. Here are my variables, Z1 through Z5. Okay, they're all standard normals. The other thing I probably want to do up here, just so I get the same simulation results every time and I'm not surprised by slightly different numbers, is set seed to 42 because it's the answer. Okay, now let's have a look at some of the other variables we need to generate to get our two-stage least squares estimator. Okay, so the next thing we probably want to do is to generate the etas. This requires a little bit of Stata's matrix language, which I'm not entirely fluent with, and was something that I don't explicitly teach in my econometrics course. So what I did was I gave my students this code here just to get my etas drawn. Okay, so in here, I'm just going to paste that in there, make sure there are no errors with copying out of my PDF. I'm guessing Stata will probably tell me. And then I can list eta in 110. Okay, so there are my etas in my data set. And I can check the correlation of my etas. If we remember, if we looked at the specification, this number needed to be about 0.8. This number needed to be about 0.2. Those are, within the simulation accuracy of those numbers, so I think we're good. It looks like the simulation is working well. Okay, now we can code up our x and y, and x, y, and z6, and we're good to go. Okay, so x is equal to 0.1, well, we need to do z6 first. Okay, so I'm going to move this over this way a bit so I can see what's going on. Okay, z6 is equal to eta 3. Now we have x is equal to 0.1 z1 plus, what was at the end here, 0.1 z6 plus eta 2, 0.1 z6 plus eta 2, and then y is equal to x plus eta 1. Okay, let's check that works. Z6 not recognized. What's going on here? Oh, I need generates here. Best way to find errors in your code is to run it. There we go. That's working nicely. Well, it's working now. Okay, so now I can start estimating these 4 models and to see how they perform. Okay, so what it's asking for is 2-stage least squares just with Z1, Z1 through 5, Z1 and 6, and then all of them. Okay, so let's estimate those. So that would be IV regress 2-stage least squares y x equals Z1. Okay, everything's going to look pretty similar to this, so let's copy that over. The next one is going to be Z1, Z2, Z3, Z4, and Z5. Okay, and then we need, so we're looking at the third one now, Z1 and Z6. So we're just changing the list of instruments here, and then IV regress, let's do this like this. We're going to use all of the instruments. Okay, so let's check that this works. Oh, it ran. That's a good start. Now, remember the true value of beta 1, we know because we generated y, right? There's a 1 out the front of here. So the true value of beta 1 is 1. And if we look at these numbers, we've got a 2. That's a bit worrying. We've got a 2. We've got a 1.3, which is a bit less worrying, but, you know, it's outside of the standard deviation of this. And now we've got something that's very close to 1. Okay, so this is the model we know is completely specified. Okay, so here we've coded up one step of the data generating process. Now we need to get it into a program. Okay, but to sort of show you what we do here, if we wanted to manually simulate this over and over again, I could just run this over and over again without resetting the seed, and I'm getting different numbers every time. Okay, but this is something your computer is a lot better at doing than you are, so we're going to get Stata to do this for us. Okay, so now I'm going to put a program around this script here, starting below set seed. Okay, so I want to tab that over a bit so I know where my program starts and ends. And I'm going to tell Stata, look, here's a program define, and it's going to be an R class, which means we're returning some scalars, and we need to tell it where the end of the program is so it stops trying to look for more things to do. Okay. And what we want to do here is to get out the right numbers from these 2-stage least squares. So here what we want to do is to return scalar, right? We're telling the function what it's going to return. Like we have some inputs. It really doesn't have any inputs, but we need to tell it what the outputs are. Return scalar. Let's call this b1 equals underscore bx. So return a scalar that's called b1, which is equal to the coefficient on x in this regression. Okay, and we just want to store these numbers for all of these regressions, right? Just tell me the coefficient on x for all of these regressions. Okay, so we can run that. Oh, I haven't given it a name. There we go, it has a name called thingy. Okay, so the program is defined, but it hasn't run yet. Okay, it's now just stored in the memory, so let's just check that it works. Looks good. Okay, so now what I need to do is so that was the second step, and just to check that things are working, I could thingy, so I run the program, and then below it, I can ask it to tell me what it stored. Okay, it stored something called B4, B3, B2, and B1. Well, here's our B4 here, right? And here it's stored this. And so what I can do now, after I've run the program, is I can access these things because they're stored in memory. So I could do something like, just as proof of concept, display B1. And there it is. Okay, so now we want to do this over and over again, say, let's see how long 1,000 times takes, and then see how the simulation, so the sampling distribution changes with these 4 specifications. Okay, so to do that, we're going to use the simulate command, which looks like this: simulate. Then you tell it how many reps. I'm just going to tell it to do 10 to start off with, because I want to make sure that it works. I actually know that it's not going to work at this point. And then we tell it the program to simulate. Okay. And if we look at this, we've got some errors here. Okay. The dot here to start off with tells me that the first simulation step worked, but everything else we had an error. And the problem we had with that was that the second time we ran this program, when we got to the top of this loop, variable z1 still existed in the memory, and Stata doesn't want to generate a variable that's got the same name. Okay, so what we're going to do here is what we'd want to do in any other part of Stata if we wanted to replace a variable name. In this case, we can just clear all the variables and off it goes. Okay, so now if I list my data set, what I have here are the betas from that last regression, which isn't exactly what I wanted. Okay, so I need to tell it to access B1, B1, and so on, like this. So I need to tell it which variables from the program it needs to access. Let's see if that worked. Nice. Okay, so there's 10 draws from the sampling distribution of these 4 estimators for beta 1 hat. Really the only good one here is this first estimator here, B1. Okay. Okay, so now that we've worked out that the simulation is working, now's the time to run the simulation with enough repetitions that we can actually trust the results. I'm going to start out with 1,000 and see how long this takes, and I might come back and run it with 10,000 if that doesn't take too long. Okay, and see it running there. I think for teaching purposes, 1,000 is going to be long enough. In fact, I'm going to pause the video and come back to you in a minute. Okay, excuse me, and we're done. So we could have a look at the results, and it's not that interesting just to look at the numbers, but here are our 4 estimators. If we remember what these were, this was just using Z1. This one was using, what was it, Z1 through 5, which were from memory, the weak instruments, right, Z2, 3, 4, and 5, failed the inclusion condition, right, they had no explanatory power for X. Then we have Z1 and Z6 being used here, so Z6 satisfies the inclusion condition but does not satisfy the exclusion condition, and then this last column is using all of them. Now just looking at these first 100 draws, or really the draws 80 through 100, hopefully what you can see here is that the estimates, I think from the first column here, look a lot better than everything else. I mean, especially this first column looks better than columns 3 and 4, where we're including Z6, which isn't a valid instrument because of the exclusion condition. But probably a better way to look at this is to visualize it. So firstly, we're going to label some variables so that our graph makes a bit more sense. So B1, we're just going to label these with the variables that the instruments we're using. B2, Z1 plus Z1, 2 through 5, which fail the inclusion condition. Label variable B3, which is Z1 and Z6, which fails. Better if this is fails inclusion, and this should be fails exclusion. And then B4, Z1 through 6, just label it like that. What we really want is the graph, right? So two-way, K density, all the B's. Would help if I spelt density correctly. Okay, so if I just run this piece of code, let's see what we've got. Might take a minute. Too many variables specified. That's okay. Stata doesn't like plotting the kernel density of 4 different variables, but I can always combine them in two-way. So let's try that again. And we have a problem here because the support of B1 here, for some reason my labels aren't working either. The support of B1 is pretty bad for one of these. So let's see if I can change the support, or the horizontal, the X range of this graph. Really, I could exclude some parts here. So say the true value of X is 1. So let's say if B1 greater than 0. Let's try that again. Okay, here we go. So here's our 4 densities. I'm wondering why my labels aren't working. Let's try this again. Maybe I need to run it like this. No, it's just not liking it. Maybe I have to label the legend or something. I think that's how I have to do it. Okay, anyway, let's put in a vertical line at the true value, so that here would have X line 1. I think that works. Yes, okay, there's the true value. And here is the kernel smooth density of all 4 of these estimators. Okay, so we've got the blue one here is just using Z1. then this brownie red thing is using Z1, 2, 3, 4, and 5. So that passes the exclusion condition, but Z2 through 5 don't have any explanatory power for X. So this one, sort of the collection of instruments here is weak. Okay, and so here we've got a upwardly biased, I think if you run the first stage, or the bivariate OLS, you get a value of 2. And then over here, these two, when we include Z6, are just terrible, right? They're, they're not on the correct value. If you wanted to look at some summary statistics, we could also, summarize the distribution without a plot. So you could summarize B's here we go. So the mean B1 is not so good. I need to have a look at that. Okay, I've worked out what that is. And so the problem I'm having is that B1, one of the draws for B1 is negative 264, which is where I had the problem with the plot. But if we look at how many observations are less than 0, how many are less than -1, how many are less than 10, really everything other than this negative 264 is greater than -10. So really what I've got here is one unlucky draw, which if you think about it, that's putting in a weight of, that's contributing roughly negative 264 divided by 1,000 to my mean here, which is moving this down by, 0.25, which is quite a lot. Okay, so what I'm going to do is I'm going to rerun this simulation. Fortunately, I know what the answer is here, but I'm going to rerun this simulation with 10 times the sample size, and then we'll see if we get the same results. Okay, so this is going to take a while. I'm going to pause my video. Okay, so I reran the simulation with 10,000 steps and didn't really change that much. And then I followed up with running it with a different random number seed, which got roughly the same results. You get slightly different numbers when you run it with a different random number seed. But what we're getting here is that the blue distribution definitely does look better than the other ones, right? So the blue distribution is where we use the one instrument that satisfies both the inclusion and the exclusion conditions. But what I've got here are the more detailed summaries of each of these variables. So if we go up to the first variable here, here's summarize B in detail. The mean is off, but if you think about this, the standard deviation is huge. Okay, so 1,000 observations with this instrument doesn't get you a particularly good estimator for the causal effect, but the median is pretty much spot on. With the others, see here, mean and median, if we use the instruments that fail the inclusion condition, that's worse. And your estimator, thinks that it's more accurate. It's centered around this incorrect mean with a small standard deviation. Then we have a look at these, and these ones are, centered around, a number closer to 2. So what I'd like to do now is just modify the program a little bit, and instead of have Z1 have a coefficient of 0.1 on here, let's make Z1 explain X a little bit more and run the simulation again. Okay, so here we have the blue distribution is looking nice and centered around the true value, but the same with the red one, which was including the weak instruments. Here the trouble is, not the trouble. What we're getting here is that the together Z1 through 5 now have a lot of explanatory power for X. So it doesn't really matter that we have these 4 instruments here that aren't really explaining X. The Z1 is doing most of the explanation on itself. So what I'm going to do now is sort of look at somewhere in between. If we go back up here, not sure what's going on there. Go back up here and put the coefficient on Z1 equal to, say, somewhere in between, like 0.2, and run that, and we'll see what happens. Okay, and there you have it. So this is with Z1 having a little bit more explanatory power for X than we did in our first example. Here we have a mean of 0.97, or 0.98 if we're rounding, which is, you know, close enough to the true value. Here, once we've got this other estimator here where we include the weak instruments, where it's not really so much of a problem here because Z1 has some good explanatory power for X. Okay, but if we go and look at our plot here, the red distribution slightly bumped up to the right, and these other two here you don't really want to touch with a 10-foot pole or anything. So thank you very much. I'm James Bland, and this has been Econometrics.